Hi there, and welcome back once again to our course in ENSC107. And from this topic onwards, we'll be discussing another set of topics, and that's about fluid machineries. Although there are many types of fluid machines, we'll just limiting our discussion to fans and blowers and also to pumps. So for today's lecture, we'll just discuss about fans and blowers, and the next day topic will be the pumps. Okay, so fans, blowers, compressors, and what else? Pumps. And actually, there's still another one, fluid machines. We call it turbine. But for fans and blowers, these are used for transport or transfer of fluid from one point to another. Okay, so that means, for example, in a pipe systems, if you want to transfer the water from, let's say, from a source to a tank, then right, so let's say here's our tank. So if you want to transfer the water from this source to that, then we use these fluid machines called pumps. Now, fans, blowers, and compressors, they're also used to transfer fluids, except that um, the fluid that's being delivered is air or gas. It's an air or a gas. This one is for liquids. Okay, so we encountered these fans and blowers in the processing equipment, like for example in flatbed dryers. And when we say flatbed dryers, that's a type of mechanical dryer wherein it's just we just dry this grain of bed right here, and this is a perforated sheet. And in order to dry this grain of bed, we need to introduce the hot air. Okay, so the hot air is being pushed by this either fans or blowers, right? So that's it. And in ventilation systems, in livestock housings, we have this. If we want to introduce the fresh air inside, then of course we need these fan systems, and this air should enter in this air inlet or maybe an evaporative cooling pads, right? So actually there's a lot of applications for these fluid machines. So again, fans, blowers, compressors. For compressors, usually you can see this in also processing equipment and what else, hydraulic and pneumatic equipments for the compressors. But we'll limit our discussions to this fans and blowers only. And for this one, for these turbines, this is a fluid machine wherein we want to extract the energy from that flowing fluid. Right, so now let's narrow in. So fans, blowers, and compressors. When we say, so here's our lecture handouts. We have here an actual fan installed in I think this is a dryer, and also this one is installed in a drying equipment, another type of drying equipment. And here's our compressors right here, and right here we have a pump. So now the difference between fans, blowers, and compressors, because they are all air moving devices or gas moving devices. So the difference is actually in this static pressure and this specific ratio. So that means that when we say fans, usually the operating pressure is lower, and let's say it's just up to 13.8 kilopascals. But for blowers, it's 13.8 to 103, and for compressors, it has higher pressure, working pressures. So that's just the main, or that's just the basic difference. between fans, blowers, and compressors. So now let's talk about the types of fans. So we have here axial fans, or types of fans and blowers rather. So we have axial fans or blowers, as centrifugal fans, and this cross flow, and there's actually another one, mixed flow, but we'll just focus our discussion in this axial and centrifugal fans. So axial fans, they're the type of fans like as shown as this one. It's an example is right here. I have a small fans, axial fans. So the air enters. So actually, for these fans and blower devices, we have this impeller. So that's the um, rotating part. So when the air enters this, and um, it's being hit by these blades right here, these fan blades, and that increases the pressure, right? So that's it. So for these axial fans, the fan enters at this side and exits at this side. So right here in our figure, it enters here at the back, and then it exits here at the front. So that's the axial fans. For centrifugal fans, it's actually a volute shape, and the air enters at this side, and then it spins. It is being spin by this impeller right here, and then it is exhausted in this direction. So the entry point is not the same, or the entry point is perpendicular to this exit direction. Right. So again, there must be an impeller right here, and for the cross flow, basically it's just changing the direction. And for the mixed flow, that refers to the mixture, something like a hybrid between this axial and the centrifugal. Okay, so now let's talk about the types of fans. So for the type of fans, we have propeller fans, we have tube axial fans, and vane axial fans. Now, when you say propeller fans, these are typical fans like for exhaust fan, right? So it's just basically consists of these impellers and this electric motor, and of course the shaft, and maybe some housings or some guards just for protection. They are used for low pressure and high flow applications, and but of course lower efficiency and running at low speed only. And when I say tube axial fans, um, it's basically something like a propeller fan, except that we have this cylindrical housing, and for this vane axial fans, it's something like this tube axial fans, except that there is a vane right here. So that vane that guides the airflow and somehow improves the properties, or the performance rather. Right. So here's our propeller fan, and if we have this cylindrical housings, that's gonna be a tube axial fans, and if we have this guide vanes, that's what we call a vane axial fans. Okay. By the way, between axial fans and centrifugal fans, right? So let's say we have this. So between axial fans and centrifugal, often said that for axial fans, this is of course, if there's airflow, then that means we have Q. That's going to be the flow rate, and we also have the pressure. And for this one, again, airflow, then that means we have this flow rate and we have this pressure, operating pressure. So it can produce more pressure, right? So for axial fans, usually they are known for high flow rate, so high flow rate but low pressure. For centrifugal fans, they have high pressure but low flow rate. So depending upon the applications, if you want axial fans or if you want centrifugal fans, and you notice that, for example, in ventilation systems, you want a high flow rate because we want fresh air. We want more pressure. Sorry, we want more fresh air. So if we want more fresh air, then what we want is this. But of course, it has to be compatible with our required system pressure. But for example, if our ventilation system for is in let's say is in ducting systems wherein there are ducts, so of course the pressure will be high, and what we may need would be this centrifugal fans. Okay, so next one is types of centrifugal fans. So the centrifugal fans looks like this. So if we draw it here in 3D, what we have is something like this. So it's a volute shape. So that means that it's not a perfect circle, but rather it's a volute. So the air enters at this inlet, and then it is being spined and then exits here. Alright, so here's our impeller, and the air enters at this side, and it is being hit by this impeller blades, and that's it. Now for the centrifugal fans, we can classify the fans based on the shape of the blades. So right here we have a radial blades, we have forward curved, we have backward curved, we have backward inclined, and airfoil. So for radial blades, you can see it that the blades are just straight, and when we say radial, that's actually passing through the center. Okay, so that's it. So here's radial blades, and when I say curved blades, then that means that instead of having straight blades, we are having a curved blades. And the forward curve is let's say has this orientation, and the backward curve has this orientation. So how do we know if it's a forward curve or a backward curve? Then we see, or we check this rotation, this direction of rotation. So of course that means that the air is being hit by this open side, whereas for backward curve, that means that the air is being hit by this back side. So that's it, forward curve, backward curve, and we also have backward incline. It's just a straight blade except that it is inclined, and we can also have these airfoil shapes. So specifically designed shapes for airflow. For best performance for airflow, I think. So that's it. So of course, the point right here is that there will be different because of these different types of impellers, then of course that means that there's going to be different types of performance. Okay, so just a couple of things right here for, let's say, radial fans. It says that it's used for high pressure medium flow application and rugged environment. It's just a simple design. But for forward curve fans, so used for medium pressure high flow and clean environment. For backward incline, I think you just have to read this. So now let's talk about the fan fundamentals. Now for the fan fundamentals, it's all about the computations regarding the fans, and of course there's still many other computations if you check the textbooks, but I just included some few computations right here. So first one is to compute the air power. So the air power is the power the air power is the energy added by the impeller of the fan to the air. So as the air, because these are fluid moving devices, these are devices that increases the pressure, and that means that when the air passes this, then there's going to be energy added into the air by these impeller blades because it was hit by this impeller blades. So that power is what we call air power. So that is to move it against a particular pressure. So AP is equal to this flow rate times this flow rate, and the this one is our unit weight or weight density. So recall that weight density is just simply the density times this pressure head. Okay, and oh, sorry, times the G, rho G. Alright, so that's it, rho G, and for the H, that's our pressure in head. So take note the pressure, it can be in kilopascals, but of course when you say head, that's we are referring to this unit unit of length. Okay, so again, air power, that's the air or sorry, that's the energy added by the impeller of the fan to the air or gases to move it against a particular pressure. And here's our equation: AP is equal to Q times this times that. Alright, so if we use this, when we use for this head term, we use the static head, then that means we have this static air power. If we use total head, then that means we are computing for the total air power. Okay, next, fan pressures. So for the fan pressures, we have this. The total fan head is the amount fork needed by the fan per specific rate of air flowing through the fan. This is just it. So the total head would be just simply consist of the static head plus the velocity head. So just the Bernoulli's equation. And for the static head, we have here the equation for the static head. So it can be in pressure, right? Recall this equation: plus v squared all over 2g plus z, right? And then another set right here of this 0.1, and then right here this 0.2. So this p by gamma, that's what we call the static head. And in terms of head forms, then we can use this. If we use this p sub 2 or p sub 1, just take note that sometimes the units used in or given in the problem is in terms of kPa, sometimes it's in terms of head form. So just check the units. Then the velocity head is this. That's the v squared all over 2g. Now in terms of physical meaning is, let's say here's our flowing fluid. Let's say it's a water or an air, for example. So how do we know, or how do we measure this static pressure? Just recall that because of the presence of fluids, there's actually a force exerting at the wall or at the bounded surface. So that force distribution is what we call the pressure or static pressure. Just simply because there is a fluid, so there is a static pressure, right? So if we install a manometer right here, and here's our manometric fluid, then of course there's going to be pressure pushing this fluid, and that's the reason why there's going to be a change in the height or in the level of this manometric fluid, right? So that measure, if we install the manometer this way, the measure that we can measure is the static pressure. That's our HS or PS, so that depends. And if we install the manometer this way, so we have here, in the direction of the flow, then what we can measure there is the total pressure, right? So that's the total pressure. And another pressure is this velocity pressure. So if we install this manometer in this way, so we have this something like the total pressure, and we have here the static pressure, and of course there must also be think there must be a fluid right here, right? Pushing this fluid, and then there is this pressure also pushing this manometric fluid. So that's going to be the velocity pressure. So again, in a flowing fluid, we have this static pressure and we also have this velocity pressure. When you say static pressure, just simply because the fluid is there, then there exists a static pressure. And because of the motion of the fluid, I mean, if the fluid is moving, then of course there's got to be energy or pressure related to this motion of the fluid, and that's what we call the velocity head. Okay, so that's it. And next one is the fan efficiency. So fan efficiency, we have here I think that's the eta, if I'm not mistaken. That's the Greek letter for eta. And this is AP, that's the air power divided by the brake horsepower times 100%. Now, when you say brake horsepower, because there's actually a lot of horsepower terminologies, even in engines and blowers and all that. So right here we have this air power, the AP. So that's the energy or power added into the air because of this interaction between the air and the blade of the fans. And when you say brake horsepower, it's actually related to this, to the shaft. That's the power right here at the shaft, right? So another one is although it's not in our lecture handouts, the horsepower for the motors, then of course there's gonna be, because there's a lot of frictional losses and all that, then that means that the horsepower for the sizing of the electric motor would not be the same as the brake horsepower. So just take note, when we say brake horsepower, we are referring to this horsepower generated at the shaft. And when I say air power, that's the air power, or that's the horsepower transferred into this moving fluid. Okay, and what else? Fan specific speed, that's another term, and it says that it is a dimensionless parameter used to describe the applications of different types of fans. Anyway, I think that we'll do a sample problem for this. Before we move on to our sample problem, I think let's have a detailed discussions regarding this fan pressure or fan head. And recall that in our lecture we mentioned that the fan pressure consists of this static head and also the dynamic head, right? So here's the total pressure. This one is the static pressure, and this one is the velocity pressure, or the velocity head, static head, and total head. Actually, if we apply the conservation of energy into these fan systems, then what we can actually is we can actually arrive into these terms, except that with some simplifications. So what do I mean by that is, let's say here's our fan. Right, so here's our impeller, here's our housing or ducting, and of course there's gonna be a flow of air. So that means that there's gonna be some input or flow that's going into the fan, and then there's also flow that's going out from the fan. So if this is my system, thermodynamic systems, then what are the energies that's crossing the boundaries? So first one, we know that we have energy coming from the flow. So let's write here flow or inflow. And also we have an outflow. Okay, so what else? Of course, we also need energy that's energy that we need to input into the fan. But of course, when we say energy right now, what we are talking about is actually in terms of head, because recall that pressure can be expressed in terms of say head or pressure and also energy, right? So I mean pressure in terms of this flow, this in this fluid flow. Anyway, so there's gonna be some input of energy or head. So let's just write there H blower, right? And of course there's gonna be losses. So let's say here's our loss HL. Okay, so if we do the conservation of energy, energy in is equal to energy out, then the input terms, actually the inflow is this one. So the pressure head P1 by gamma plus V1 squared all over 2G plus Z1, right? So basically the energy, the Bernoulli equation. And right here we also have P sub 2 by gamma plus V sub 2 squared divided by 2G plus Z sub 1. So those are the energy terms or the head terms in the inflow and outflow. So if you substitute that, what we get is P1 plus V1 squared all over 2G plus Z sub 1, right? That's our inflow, plus the blower, H blower or fan, right? Is equal to the outflow of P sub 2 by gamma plus V2 squared all over 2G plus Z sub 1, right? Plus the losses. Okay, so that's it. So now I just would like to isolate this term right here. It is H blower in the left hand side, and therefore I will transpose this to the right hand side. So if I transpose this to the right hand side, what I get is P sub 2 minus P sub 1, and V sub 2 squared minus V sub 1 squared, and Z sub 1 minus, Z sub 2 minus Z sub 1. So let's do that. H blower is equal to P sub 2 minus P sub 1, right, plus V sub 2 squared minus V sub 1 squared all over 2G plus Z sub 2 minus Z sub 1 plus HL. Alright, so these are my terms, and recall that this is just simply what we call this looks similar, this one looks similar to the notations that we used right here. So when we say total head, that's actually the head for the blower, and the static head actually refers to this one. So this is static, and for the velocity head, this refers to this one, or dynamic, static or dynamic head. Okay, and this is actually negligible. The pressure difference with respect to elevation actually is negligible because we have a fluid that has a lower density, so therefore it can be neglected. So this is approximately 0. And if we don't have any losses, let's say we only consider this, unless we consider a ducting systems, then of course we need to, if we have a ventilation ducts, for example, then we have to consider this. But for now, let's say this is 0. So the point right here is that this H blower, this static, is actually what we call HS plus HV, and this one is H blower, is equal to this. right? So they are equal, of course, with some simplifications right here. So again, this is only true. The elevation is negligible if our fluid is an air or a gas or a fluid with a low densities. But in terms of, let's say, in pump systems, later on, what we'll see is this one we include this, but this one gets to be the zero term depending upon the system. Anyway, we will discuss that. So that's just the point of our detailed discussions or derivations regarding this fan pressure. So if we don't remember this, then let's just apply the conservation of energy and then make some simplifications. Right, so I guess we are now ready for our first sample problem.